Hi there, welcome to lecture 4 in Fox, and today we're going to be talking about proofs. Okay, but before we start, let me remind you where we were from last time. Last time we talked about how to make precise statements. Basically, we talked about formulating all our statements using sort of propositional logic, augmented with quantifiers. So propositional logic is you have your basic statements, you have not, and or, and the other main tool is the if-then, the implication. And then we augmented that with quantifiers such as for all and there exists, which allow us to make statements about an entire collection of objects. So it's important to be able to formulate precisely what we want to prove. And today we're going to be talking about proofs. Okay. So the main thing we're going to be focusing on is the if-then, the implication. So how do you prove an implication? Proving an or proving an and are relatively simple. To prove an or, you prove that one of the two things is true. To prove an and, you prove that both of the things in the and are true. But to prove an if-then, that's a little bit more complicated. We're going to spend a lot of time on that. Okay? We're going to develop proof patterns for if-then. And related to if-then is this notion of equivalence, and then we'll sort of talk about another very, very deep proof technique. It's the proof technique we used to prove that the square root of 2 is irrational, and that's contradiction. We'll talk about proving things about sets, and we'll conclude with a sort of a template of when you're faced with a situation where you need to decide how to prove something, what kind of proof should you make. Okay, so implication, that's what we're focusing on for the moment. And let me contrast this notion of an implication with something that we are familiar with in everyday life, which is reasoning. So I came to you and I told you, last night it rained. So that's a fact. You know something. It rained last night. And from this fact, you will deduce that the grass is wet. And that's a everyday chain of reasoning that we're very familiar with. You have no problem with this because of all the wealth of experience you have in the real world. So if I tell you this fact that it rained last night, then you deduce that the grass is wet. So that's everyday reasoning. Contrast that with an implication. Okay, so here's an implication. If it rained last night, then the grass is wet. Now, why am I spending such effort in contrasting this? Because I'm going to ask you the question, well, what do we know? Did it rain last night? We don't know. Is the grass wet? We don't know. And so this is sort of, could be viewed as a flaw with the implication in the sense that it doesn't really tell you anything. Okay, so there are no facts that it tells you. So I'm going to call this reasoning in the absence of facts. Okay. It's not telling you anything, but what it is doing is important. It's linking two things together. It's linking the statement, it rained last night, to the statement, the grass is wet. Okay. It's essentially stating the validity of the tool that we used in the previous reasoning example to conclude that the grass is wet. And so that's the value of this link. The value of this link, the value of this reasoning in the absence of fact. So the value of sort of showing that this implication is true is that if sometime later someone comes to you and says, you know what, it rained last night, you can immediately conclude the grass is wet because we have established the truth of this implication. So that's the value of implications. And now let me show you some sort of more concrete applications of implication in the context of computer science and math in general. So, so here's a claim. Okay, it's an implication. So what it does is it links two things together. And we're not in a stage where we can prove such a claim, but supposing we did. So if we can quickly find the largest friend clique in a friendship network. So we talked about friendship cliques, groups of people who all mutually know each other. So you have a social network like Facebook with 3 billion people. Okay, what's the largest friendship clique? So what's the largest group of people who all mutually know each other? If we can find that quickly, well, here's another problem that we sometimes like to solve. So you have a bunch of radio stations, so many radio stations in the US, they're distributed all over the place. Well, how do we assign non-conflicting frequencies to these radio stations so that nobody hears garbled music? And well, the challenge here is that, well, certainly I could assign a different frequency to each radio station, but I want to assign frequencies as few frequencies as possible, because I want to use a limited amount of bandwidth. So these two problems look completely unrelated. But imagine if I went and proved the implication that if I can find the largest French fleet, then I can find non-conflicting frequencies for radio stations efficiently. So if I can do one, I can do the other. Now, can I find large friendship fleets? No. Well, we don't know. We haven't established that. Can I find non-conflicting radio frequencies for radio stations? No, we don't know that. It's just like if it rained last night and the grass is wet. Very similar. Okay? We don't know anything. We've just established a link. This is a very powerful link. So it means that, for all those of you who want to establish to assign radio frequencies efficiently, you don't need to solve that problem. If someone else has been able to find large friendship fleets in graphs, you can just take what they did and use it to solve your problem. That's the value of this link, the value of this reasoning in the absence of facts. Here's another example that's familiar to you from high school. Okay. So, in high school you learned this quadratic formula, this beautiful thing. Well, let me formulate it in the form of an implication. Okay. So, at the moment we don't know anything, and what we're saying is that, if, okay, now I'm going to link two statements together. That's what an implication is. If ax squared plus bx plus c is equal to 0, okay, and a is not equal to 0, okay, so, if you are in a situation where this is true, okay, then you can conclude that x equals, minus b plus or minus the square root of b squared minus 4ac over 2a, okay, this famous quadratic formula. So what that says is that, it doesn't really say anything. It links these two. It says that if sometime in the future someone comes to you and says, I have an x and it satisfies this equation in a non-trivial way, that is with a not equal to 0. It satisfies this quadratic equation. Oh, then you can come and say, but Malik proved this implication, this link that says that whenever this is true, then we can conclude that x is either this number plus or is minus b plus or minus the square root of b squared minus 4ac over 2a. Okay, so that's the value of these implications. You use them all the time. It may have not been taught to you formally as an implication. It was taught to you as the quadratic formula, but in reality, it is an implication. And that's why we prove implications, because we'll use them later when someone comes and reveals to you a new fact that establishes that the left side of the implication is true, and you conclude that the right side is true. So there's a huge value in proving implications, even though they may not give you any new facts, any new knowledge. It proves relationships between. Okay. So today, we're mainly going to focus on proving implications. Okay, and then we'll talk about, contradiction as another powerful proof technique. And lastly, we'll talk about proofs about sets. Okay. And as usual, when it comes to math and writing proofs and so on and so forth, we're going to move to the board. Okay, so I'm going to be telling you about some proofs, and starting with proving implications. Proving implications means the truth table for implication is extremely important. So I'm going to write it down. Okay, so P implies Q. P implies Q. That's implication. And if I'm looking at the truth table, we'll list the possible values of P and Q. So we saw this before, so I'll do it very quickly. Okay, so P, Q can be false, 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 true, true, false, true, true. Okay, and the implication is only false in the event that you find a situation where P is true and Q is false. So here it's false, and here it's true, true, true. This is so important, I'm going to box it as a reminder to Malik, don't erase. Box, not erase. Okay, and this row in which the implication is false is also going to be very important, so I'll highlight that row. Okay, so this is the row in which this implication is false. Okay. And so let's talk about proving implications. And I'm going to start with two examples of implications. So the sum of two rational numbers is rational. Okay? Example number 1. And example number 2. every even square came from an even number. Okay. So the first thing I want to note is that these are implications, and it may not look obvious that they're implications. So at the moment they're just claims that have been stated in English. So let's convert them to implication and the mathematical language that we talked about last time. So the sum of two rational numbers is rational. Basically what we're saying is that if you have two rational numbers, so if x is rational, so q is the set of rational numbers, x belongs to q. So if x is rational and y is rational, then x plus y is rational. Okay, so the sum, if x and y are rational, so if x and y are two rational numbers, then their sum is rational. Okay, we can further sort of simplify this or put it in more mathematical notation by observing that we'll call this q, p, we'll call this q, and then this is saying that, x, member of the rationals, and y, member of the rationals, implies x plus y is a member of the rationals. So x and y are rational, implies x plus y is rational. Okay, we'll do the same thing here. What do we say? Every even square. So if you ever happen upon an even square, so if it's a square, so if n squared is even, okay, so every even square came from an even number. What they're saying is if you come upon an even square, it must have come from an even number. So if n squared is even, then it must be the case that n is even. Then n is even. So I've taken an English claim, put it into an if-then form, and now I'm going to make it more mathematical by saying that this is basically the compound proposition or the implication. N squared is even implies n is even. Okay, and in this case, this is p and this is q. We have p implies q. P implies q. And now we're going to address the issue of how do we prove these claims? How do we prove these implications? And okay, let me first step back and sort of address something that might be a little bit scary at the moment. Okay, what is scary at the moment? I'm asking you to prove something, okay, and it's this something that involves x, y, or in this case n, and we actually don't know anything about the variables that are involved. So I'm asked to prove this claim. X is rational and y is rational implies x plus y is rational. Well, what is x? Don't know. What is y? Don't know. Are x and y rational? Don't know. What we're asked to prove is a link between two claims. That's what an implication is, and that's what makes it subtle and hard to prove. Okay, for example, here, what is n? We don't know. Is n squared even? We don't know. All we're saying is that if you ever end up in a situation where you have an n squared that's even, it must be the case that n is even. So there's this link. But I don't know at this moment what is n. I don't even know if it's even. I don't even know if n squared is even or odd. Okay? And we will never know. All we're doing is proving a link. Reasoning in the absence of facts. We have no facts. We're just proving a link. Okay. So how do we prove it? How do we prove such a link when we don't know anything about x and y? And that's where the truth table comes in. It is absolutely fundamental. Okay? So we're asked to prove that an implication is true. Okay? So we'll look at the truth table and see when is it true. So it's true, true, true. Here's the situation where it's false. So equivalent to proving that it's true, we may show that it is not false. Okay? And because there's only one situation where it is not false, proving that it is true essentially amounts to showing that this situation cannot occur. This row in the truth table cannot occur. To prove P implies Q, show that this row cannot occur. That's a fundamental idea. Okay. Fundamental idea. Okay. So let's see how that can work when we don't really know anything else about x and y or x plus y in this situation. So how do we show that this row cannot occur? Okay. So step one. In this row, it is the case that P is true and Q is false. So, step one. Let's see
what happens if P is true? If P is true. Are we saying P is true? No. We're just saying, let's see what happens if P is true. Imagine I jump into a fictitious world, okay, and in this fictitious world, it so happens that P is true. So I arrange a fictitious world. I'm pretending that P is true. I'm not claiming it's true. I'm just pretending it's true. Okay, what does that mean? What does that mean? Well, if P is true, in this case, P is the claim that X and Y are both rational. It means that X is rational and Y is rational. What does that mean? That means that X equals a ratio, A over B, and Y also equals a ratio, C over D, where A is an integer, B is a natural number, and that's nice because B is in the denominator, it cannot be 0, and that's one of the advantages of the natural numbers starting at 1. So it's 1 and bigger. So B is a natural, and C is an integer, and D is a natural. So that's what it means. If I end up in a world where P is true, that's what it means. Okay? Now, what does that say about Q? Why am I even worried about Q? Because I'm analyzing this row in which, the implication is false, and in this row, we start off with by being in a world where P is true, and then we ask, what does that say about Q? Okay, so let's see, what does it say about Q? Well, Q is a statement, a claim that or proposition that involves X plus Y. So we have to look at X plus Y. So X plus Y. Well, what is X plus Y? It's A over B plus C over D. Is A over B plus C over D, and we all know how to do basic high school algebra. This is A, D plus B, C over B, D. But look, B and D are natural numbers, bigger than 1. So the product is a natural number. Okay, so this is and A, D, and B, C. A, D is A and D are, A is an integer, D is a natural number, so the product is an integer. B times C, again, product is an integer, so the sum of two integers is an integer. So I'm relying on your high school math to sort of inform you that the top guy here is an integer and the bottom guy here is a natural number. Okay? But that is exactly what it means to be irrational. So X plus Y, so X plus Y is irrational. That's what it means. Okay, but so why did we analyze X plus Y? Because Q involves X plus Y. And so what does the fact that X plus Y is rational ultimately say? It ultimately says that Q, the proposition that X plus Y is irrational, Q is a true statement. This says that. This says Q. Okay, now, do we have a choice? No. It must be true. So let me summarize what we have done. We went into this fictitious pretend world in which, we have constructed this world where somehow P is true. Okay, but that's the only sort of fictitious thing we did. Then everything else here is basic algebra, and we end up with this conclusion that Q must be true. Okay. So we've tried to construct a world in which P is true. Okay. We end up showing that in this world Q must be true. So what does that mean? That means a world with P true and Q false is not possible. Now that is very interesting. So if a world with P true and Q false is not possible, it means that there's no world in which this implication can be false, because this row is not possible in any world. Because in any world where this row is possible, P must be true, but then Q must be true also, cannot be false. And so that proves that that implication is true, by proving that the false row cannot happen. End of proof. So now let me summarize what actually went on here. If you look at what effectively went on here, I sort of, by jumping into this world where P is true, I assumed P is true. And then I did blah, 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 and then I came out and showed that Q must be true. Showed Q must be So that's effectively what happened. So I could have said, assume P is true and show Q is true, but I didn't want to use this language like, assume P is true. Sort of, you'll get suspicious. I'm assuming something. Am I allowed to assume things? No, you're not allowed to assume things. And we're not assuming anything here. It's just effectively the same mechanics. Okay? What I did was I said, let me try and construct a world in which this row occurs, where P is true and Q is false. So, in such a world, let's see what happens. Okay? In such a world, P is definitely true. Okay? And in this world, you end up with an inescapable, undeniable conclusion that Q must be true. So the world in which true-false occurs is not possible. Okay. This type of proof of the implication is what we call a direct proof. And now you might wonder, well, it's kind of like, we just use the truth table. Why do we need to give it this name, direct proof? Well, we don't. Okay. It's just convenient to have a name for such a proof which is going to occur and recur and recur and recur, because, then when you're talking to the mathematics world, you will say, I am going to prove this using a direct proof, and everybody knows that what you're about to do is jump into a world where P is true, and then logically derive the fact that Q must be true. In fact, in the expert professional world, at step 4 is where the proof ends, because you don't need to then make the obvious conclusion that, this world with P true and Q false cannot occur. We don't need to take that extra step. All the mathematicians know that you're trying to show that this row in the truth table cannot occur. Okay? Now, I showed you this proof. It's summarized as a proof template in the text. So, if you want a proof template, look at the text. Okay, let's do another example. Okay. So, we're going to prove this implication. And, the idea is exactly the same. Okay. We fundamentally look at this truth table, look at this row, and show that this row cannot occur. Okay. So, even though I'm going to claim that I'm doing a different proof technique, and you'll see in books that it's a different proof technique, it is the same proof technique based on this truth table and based on the fact that what we're going to try to do is show that this row cannot occur. Okay. And you might have guessed that there must be some other proof technique if we're giving this a proof technique. So there's not just one way to prove an implication. I'm going to show you another way, but it's the same high-level idea, just a slightly different approach, different perspective, different mechanics. So, I want to enter this world, okay, where I'm trying to show that, if I'm trying to show that this row cannot occur. So let me see what happens if I'm trying to construct this row. Okay, so I'm going to enter a world, and I'm going to look at it from a different perspective. Here I assume that P is true. Let me consider the situation where Q is false. It's the same type of world I'm trying to analyze. A world in which this row is occurring. So in this world where this row occurs, Q is false. So let's see what happens if Q is false. So step 1. Let's see what happens if Q is false. So I'm entering this fictitious world where Q is false. What does that mean? So we look at what Q is. Okay. So what does that mean? Okay, it means that, since Q is false, N is not even. So if N is not even, it means that N is odd. And we know from our previous discussion of odd and even numbers, this means that N is equal to 2k plus 1, where k is an integer. Okay, so that's what it means. That's what it means if I'm trying to construct a world, and in this world, I'm imagining, I'm pretending that Q is false. It means that N is odd. It means that N is 2k plus 1. So what does that say about P? What does that say about P? So let's see, what's P talking about? P is a claim about N squared, so let's just compute N squared. So N squared is equal to 2k plus 1 squared is equal to 4k squared plus 4k plus 1. Okay, so we've computed N squared, and we see that P is making a claim of the evenness. It's a claim about the evenness of N squared. So I should try to factorize this, as a product of 2 times something. So this part is divisible by 2. So this is equal to twice k squared plus twice 2k squared plus 2k plus 1. 1. So it's twice something plus 1. But that means that this thing is odd, because it's twice something plus 1. So this is odd. So n squared is odd. And so in this world, in this pretend world, I'm trying to construct a world, and I've constructed this pretend world where q is false, because q is false here. In this pretend world where q is false, it is not possible for n squared to be even, i.e. n squared must be odd, i.e. p must be false. N squared is odd, so p is false. What is the conclusion? A world in which q is false and p is true is not possible. A world with q is false and p equals true is not possible. And if this world with q false and p true is not possible, it means that the implication being false is not possible. And so therefore the implication is true, proved. Now this fifth step, we typically don't write it in the proof, because mathematicians is obvious. Again, you will observe that the high-level idea, emphasizing the high-level idea, is the same. It's based on this truth table, showing that this row cannot occur, but the mechanics are slightly different. In this situation, you start with the world in which p is true, and you show that q is true. In this situation, you assume q is false and show p is false. Okay. So that's the difference in the mechanics. Okay. Here you assume p true, show q true. Here you assume q false, show p false. This method of proof is called a proof by contraposition, or a proof of the contrapositive. And, okay, that's the name of the proof, the technique. But the idea, the high-level idea of both these proof techniques is the same. The advantage of knowing the name is if you see somewhere, I'm going to prove it by proving the contraposition, or a proof by contraposition, you know this is what's going to happen. You're going to enter a world with q false and show that in this world, p must be false. Okay? Now, I want to emphasize again, they're the same proof technique based on this row of the truth table. So you're sitting in the exam and you have to prove an implication. What do I use to do? Am I going to assume that p is true and show q is false? Am I going to assume that q is false and show that p is true? How do I do it? What's the mechanics? I forgot. What is it? No. Okay. Don't panic like that. Go back to the truth table. Okay? And that's the fundamental reasoning behind proving an implication. When you look at this truth table, you will see that, okay, I have to show that this row cannot occur. Two ways to show it. Pretend like I'm in a world with p true and show that this cannot happen, so I must show that q is true. Pretend like a alternative approach. Pretend like I'm in a world where q is false and show that this cannot happen, so I must show that p must be false. Direct and contraposition proofs. Okay. There are other ways to prove implication. You can pretend you're in a world where p is true and q is false. So try to construct a world where this row occurs. Okay, and if you do derivations and show that all kinds of nonsense breaks out, then that such a world is impossible. That's a proof by contradiction of this implication. We won't get into that at the moment. We haven't even talked about contradiction yet. So there are, other even more powerful ways. Okay, so practice. The speed erase. Woo, 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 woo. All right. Look at that. Okay, practice. So prove. If 4 to the x minus 1 is divisible by 3, then 4 to the x plus 1 minus 1 is divisible by 3. Okay? Yes. P is Q. So it's slightly harder than either of the ones I did, but that's why it's practice. and do the practice. Now, if you're having difficulty, this is covered in the text. Okay, but let me just illustrate this implication in action. So let's consider the example. Let's consider a world in which x equals 2. Okay. So let's look at what's p. So what does p talk about? P talks about 4 to the x minus 1. So 4 to the x minus 1 is 4 squared minus 1, which is 16 minus 1, which is 15. And that's divisible by 3. Okay, so p is true. Okay. Now, if this implication is true, remember, we argued that if the left side of an implication, of a true implication, if you know that the left side is true, then the right side must be true. Okay? If the implication is true. If the left is true, the right must be true. So let's look at Q. So Q is making a statement about 4 to the x plus 1. So that's 4 to the x plus 1 minus 1, which is 4 cubed minus 1, which is 64 minus 1, which is 63. And look, 63 is divisible by 3. In fact, 3 goes into 63 21 times. Okay. So divisible by 3. So Q is true as expected. That's that implication in action. But now you're asked to prove the implication. So you have to prove it. You have to prove that this row cannot occur for any choice of x. That if this side is true, then that side is true. Now at the end, are you going to know whether this side is true? No. Okay. Reasoning in the absence of facts. Are you going to know what x is? No. Okay. And that's what's subtle about proving such implications. Okay. You have to sort of approach it in this general way where the goal is to show that this row cannot occur, and then you pretend that, for example, if you're using a direct proof, pretend that you're in this world. So that means that P is true. What does that mean? What does that say about Q? And does it imply that Q, does it show that Q is true? Okay. So that's practice. Okay. Let me now consider disproving an implication. Disproving implication. Okay. So let's consider the following implication. If x squared is bigger than y squared, then x is bigger than y. So x squared and x and y are integers. So x squared greater than y squared implies x is bigger than y. So I claim that this is not a true implication. And for it to be a true implication, it must be the case that this row can never happen no matter how you choose x and y. If you find a single world, a single situation where this row occurs, the implication is not true in general. Okay? So let's see. Consider x equals minus 8, y equals 2. So this is P, this is Q, and we have P implies Q. So let's look at P. So P is talking about x squared versus y squared. So x squared is 64, question mark. And y squared is 4. And is it greater than? Yes. So P is true. Okay. Now let's look at Q. Q is talking about x versus y. So minus 8 greater than, question mark, 2. And that's clearly false. No. Minus 8 is less than 2. So Q is false. I've managed to find a world. I've managed to find a situation where this row has occurred. P is true, Q is false. That means that the implication for that world is false, and if it's false for any world that we can construct, then it's false in general. Okay. So this implication is false. And you can think of such implications written in this way as saying for any x and y. So they're implicitly quantified. Okay. So it's false, and the way we showed it's false is to find a single world in which it is false. This is called a counterexample. A single counterexample suffices to show that an implication is false. Okay. Let's talk about equivalence. We discussed equivalence last time. So let's talk about it now in the context of proof. And to help our discussion, I will add to this very important truth table, I will add the truth table for equivalence. P is equivalent to Q. Okay, and what that means, okay, is that whenever P is true, Q is true. So they must either, for the equivalence to be true, they must either both be true or both be false. So it's a tight link between P and Q. The implication is also a link. It says that if you know, if the implication is true, then if you know that P is true, you can conclude that Q is true. Okay, if P is false, you don't know. Q can be false or true. The equivalence is tighter. It says that if P is false, you can also conclude that Q is false. So the implication is true. The equivalence is true here and here when they're both false or both true. Otherwise, the implication is false. Okay. Now, we talked about using implications in definitions. So, for example, define a U.S. citizen, defining parallel. Okay, it allows us to shorten language, shorten our communication by using, let's say, a single word like parallel, defined as equivalent to a much more complex, much more intricate concept. Okay, so let me show you an example of a definition, but this time examples of definition, but this time with sets. Okay, so we say that A is a subset of B. Okay, and that's equivalent to saying. So this is true if what is on the right is true. That's equivalent to saying that everything in A is in B. Or if something is in A, if X is in A, then X is in B. Or that i.e. X is in A implies X is in B. So the subset relationship is an implication. It says that if something is in A, then it's in B. Now, we shorten this, as I mentioned before. We usually say if and only if when we make definitions. If and only if. And then we shorten that even more. And we say, we usually shorten this to IFF. Oh, and now it's, we've densified, we've condensed it. And why do we do this? Oh, because it makes things shorter, but now, it confuses the hell out of anybody who's not a mathematician. So you look at this IFF and all this confusing and dense, stuff and all written close together and so on. And it looks daunting. No, it's just a language. So once you learn the notation, it's just a language. It's the concepts that matter. Now, here's another definition. The set A is equal to the set B if and only if, so it's equivalent to saying that everything in A is in B and everything in B is in A. Everything in A is in B says that X is in A implies that X is in B. Everything in B is in A is the same as saying X is in B implies that X is in A. Okay, and together, we have this if and only if this equivalent symbol. Together, this is the statement X is in A if and only if X is in A. So set equality corresponds to an equivalence. It says that it corresponds to an if and only if. So X is in A if and only if X is in A. Now, this is equivalence is a tighter link than implication. And if you're asked to prove equivalence, it's harder. How much harder? Let me tell you. Twice as hard. Here's why. Because for an equivalence to be true, this row cannot occur. So equivalence is true. So it means that P equals true and Q equals false cannot occur. Okay, so that means that you have to show that this row cannot occur. But if you show that this row cannot occur, that means that P implies Q is true. Okay. But also, this row cannot occur. So P equals false and Q equals true cannot occur. Okay. And this row not occurring is saying that the row with Q true and P false cannot occur. That says that Q implies P is also true. Is also true. So equivalence is true means that both of these implications are true. So to prove the equivalence, you prove both of these implications. Okay. And that's why it's twice as hard. And remember, in an implication, order matters. So these two are not the same implication. If I'm dead, my eyes are closed. If my eyes are closed, I'm dead. Two very different statements. So Proving this doesn't prove this. You have to prove these two separately. So, proving an equivalence means prove two implications. You have to prove one, that proving an equivalence P if and only if Q, you have to prove one, P implies Q, you have to prove two, Q implies P. And you can use whatever method you want to prove either of these. They can be proved totally separately. You can use direct here and contraposition here. You can use direct. You can use any method of proof for an implication you want. So let's do an example. So let's consider two integers, x and y. So x and y are integers. You could say x and y belong to the set C. Now, here's an equivalence. Here's an if and only if. xy is odd if and only if, so we'll say IFF, so that nobody else but mathematicians can read. Don't worry, you can read. Anyone can read as long as you know what IFF means. If and only if, equivalence. X is odd if and only if both x and y are odd. Okay? Now this is an if and only if it's an equivalence. So to prove it, we have to prove two implications. So we have to prove two things. One, if this is P, x and y are odd, this is Q. Both x and, if xy is odd, that's P. Both x and y are odd, that's Q. So we have to prove P implies Q. Okay, so that means that xy is odd implies x and y are odd. And we have to prove that Q implies P. So these are two separate implications. So let's prove it. So let's prove P implies Q. So we have two techniques available, direct and contraposition. It turns out that this is easier to prove by contraposition. So let's see what happens if Q is false. So contraposition. Let's see what happens if Q is false. So Q is false means both x and y being odd is not true. It means one of them is even. If one of x and y are even, then this is the product of an even number times something. Okay? So then xy, so let's see what that says about P. So xy is, so Q is false. That means x or y are even. One of them is even. So that means xy is the product of an even with something. So now high school math, when you take the product of an even number with anything, any other kind of number, the result is even. So xy is even. And so what that says is that, P is saying that xy is odd. So what have we learned about P in this world where Q is false? It means that P is false. P is false. And that's the end of the proof of this implication. So the world with Q false and P true cannot occur. That's the end of that proof of this implication. But now we have to prove two things. We have to prove Q implies P. So we have to prove that if both x and y are odd, then xy is odd. Okay, and we're going to use it direct. Okay, so if x and y are odd. So let's see what happens if Q is true. Okay, let's see what. So assume. Okay, so now I'll put it in the shortened form instead of pretending to go into this world. Assume Q is true. Because I'm proving Q implies P using a direct method. Okay, so what does that mean? Q being true means that both x and y are odd. Well, what does that mean? That means x is equal to 2k plus 1. Okay. And y is odd, but does not necessarily have to equal x. So y should equal, let's say, 2s plus 1, where k and s are integers. So they're both odd, but they could be equal to different odd integers. So this is 2 times something plus 1. This could be 2 times something else plus 1. then what does this say? So this is what it means for Q to be true. What does this say about P? It says that so P is talking about xy. So xy is equal to 2k plus 1 times 2s plus 1, which is 4ks plus twice s plus k plus 1, which is equal to twice 2ks plus s plus k plus 1. So it's twice something plus 1. That's odd. So this is odd. Okay. So if xy is odd, what does that say about P? It says that P is true. P must be true. So a world in which Q is true and P is false cannot occur. The implication is proof. End of proof. And now we have proved the equivalence. We have proved that xy is odd if and only if x and y are odd. And the proving of this equivalence requires us to prove two implications. And in this case, you have to prove those two implications separately. And in this case, we even use different proof mechanics to prove the implications. Here we use contraposition. Here we use direct. It's perfectly fine. Okay, but both of these are ultimately the same high-level proof. Okay? They are based on showing that this role cannot occur. That's the most fundamental idea I can communicate to you. Now, practice. Let me give you a practice. Okay, prove that n squared is divisible by 3 if and only if, okay, so it's an equivalence, if and only if n is divisible by 3. I will have to think, how do I prove each of the two implications that I need to prove? If you're having difficulty, look in the text. Okay. Meanwhile, I will speed erase. This time, I will speed erase everything because we're moving to a new topic. Boom, 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 new proof technique. Ow! Look at that. Contradiction. Contradiction. Okay, let me tell you about contradictions. Here are examples of contradictions. 1 equals to nonsense. Contradiction. So contradiction is nonsense. Okay. Here's another contradiction. N squared is bigger than n. N squared is less than n. Where n is, let's say, a natural number. Okay. So n is a natural number. Okay. This could be true depending on what n is. So if n is a natural number, this is nonsense, not possible. False. Okay. The absolute value of x is less than x. Never possible. Okay, not for the real numbers. X is greater equal to 1 and x is less than 1. Nonsense. It's not possible for x to be both greater equal to 1 and less than 1. Now, this is the typical type of contradiction. If you think of this as a statement P, then this is exactly the statement not P. And so what I'm claiming here is P and not P. That's the prototype contradiction, where you claim something and you also claim its negation. Nonsense. It can never be true. So these are examples of contradictions. I'll call them fishy. They smell bad. Okay, contradictions. Fishy. Okay. Now, fun fact. Mathematics is what we like to think it's consistent. Okay? So what that means is we built an axiomatic system, which we call mathematics, in which you can only prove true things. Okay? So that's a fundamental sort of goal when you build a consistent mathematics, and our mathematics is consistent. So you can only prove true things. Okay? So now let's say you're deriving something. You're going along and blah, 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 blah. And now you end up at proving something that's not true, something that's a contradiction. Okay? So you've ended up at something fishy. Okay? Now, since in mathematics you cannot prove fishy things, you cannot prove false things, it means something is wrong in your derivation. So that leads us to the principle of contradiction. So the principle of contradiction. So if you derive something fishy, if you derive something and I'm going to put it in red, fishy. Okay. Then you can immediately conclude there's something wrong in your derivation. At least one of the steps in your derivation is wrong. And then at least one step in your derivation is wrong. And that seems kind of obvious, right? If you derive something wrong, if you derive something fishy, then somewhere along the line you have made a mistake. Now, this principle of contradiction might seem self-evident, but be careful. Once you give me this principle, it's going to provide for me a very general, very powerful, but also very dangerous method of proof. So let me show you this proof. So once you give me this principle, it's given me this very powerful, general, dangerous method of proof. Let me show you this method of proof in action. So let's prove some things. So, theorem. Here's the general way in which a proof by contradiction works. Theorem. The square root of 2 is not in the set of rational numbers. So that's the mathematical way of saying the square root of 2 is not rational. So here's the way a proof by contradiction starts. And this is why it is so absolutely general. You can use it to prove anything. So I want to prove this, and I don't know how to prove it. So the method of contradiction says, well, in that case, try contradiction. So here's how contradiction works. You want to prove this? Well, go into a world in which this is false. Okay, just like we were proving an implication. So go into a world where this is false. So step 1, for anything you're trying to prove, go into a world where the theorem is false. Or the result, whatever it is. So if this is false, that means that, the square root of 2 is a rational number. Okay, now let's do stuff in this world. Okay, so let's explore this world. That's the next step. Explore this world. Well, in this world where square root of 2 is rational, what does that mean? So in this world, if we're exploring, it means that, square root of 2 is, A star over B star. And this is, we discussed this last time, and this is known as putting a fraction in its lowest terms when you took high school algebra, okay, where, this fraction is in its lowest terms. If it's rational, you can write it as a fraction in its lowest terms. And we proved this before using the well-ordering principle, where A star and B star have no common factor bigger than 1. And now I'll go through the argument quickly. So we're still exploring. We're just doing random mathematical manipulation. It's just that because I know where I'm going, my exploration is quite direct. But in general, in a proof by contradiction, your exploration can meander a little bit. And what's the goal? Yeah, I'll show you what the goal is in this exploration. So this means that A star is equal to square root of 2B star squared, to B star. That is, if I square both sides, A star squared equals 2B star squared, because the square root of 2 squared by definition is 2. Okay? And this means that A star squared is even, so A star is even. Remember we proved this before. Any even square came from an even number. If A star is even, this means that A star is equal to twice some other integer. So plugging twice k into here, this means that, 2k is equal to square root of 2b star, squaring both sides. So 4k squared equals 2b star squared. Dividing both sides by 2, we get that b star squared, which tells us that b star squared is equal to 2k squared. Or b star is even. B star squared is even. And if a square is even, it means that the number itself must be even. So B star is even. Okay, so now we've explored and done such and such and such. We've come up to a point where we've observed that A star is even and B star is even. So A star is even and B star is even, that is, they have a common factor 2. They have a common factor 2. And I'm going to underline this. Okay, and I claim that we have a prototype fishy situation where I've said something and then I've said something that directly contradicts that. So what did I say? First, A star and B star have no factor bigger than 1. And now I've meandered in this world, I've explored, and I've discovered that A star and B star have a common factor 2, which directly contradicts that, and this is fishy. And now we go back to the principle of contradiction, which says that, the moment you have derived something fishy, and that was the goal of the exploring. And you might ask, well, how did I know to explore this way and that way? Well, that's the creative, difficult part in a proof by contradiction. Okay? But the goal of the exploration, the goal of the mathematical derivations is to get to a situation where you clearly have something fishy. And sometimes you have to argue, you have to show why is it fishy. In this case, it's kind of obvious why it's fishy. Okay? And once you get to something fishy, now we invoke the principle of contradiction, which says that the moment I have derived something fishy, something is wrong. Okay? So let's go and look at all of our steps. Well, 5 clearly follows from 2, okay, because from 2 and from 2 and 4, because from 3 and 4, where here we say A star is even, here we say B star is even, so therefore they have a common factor 2. And this step 2 is a direct consequence of the well-ordering principle. So if you say that this step was wrong, you have to give up the well-ordering principle, which is an axiom. Okay, if you say, and then once we have this, all of this is basic algebra, so all of this is correct. All of this is correct. So that's very important, that my explorations, my mathematical derivations have to be correct. So, but something has to be wrong in this proof. That's the principle of contradiction. And what could it be? Well, the only thing that could be wrong is this first step. Go into a world where the theorem is false. It must be wrong. In other words, there must not be a world in which the theorem is false. And if there cannot be a world in which the theorem is false, then it means that the theorem is true. So this is the flawed step in this derivation. So this is flawed. Okay. And if that's the flawed step, then you cannot go into such a world, in which case every world has this theorem true. Okay. Now, let me summarize this proof mechanics. Okay. And that concludes the proof of the theorem. Let me summarize the proof mechanics. Basically what I did is I assumed the theorem is false. And so you can do this with anything. That's why it's so general and so powerful. Okay. So I assume theorem false. Now I explore, which means do valid mathematical derivations until you get to something fishy. So this has to be valid. The moment you have obtained something fishy, and since everything here is valid, it must be that the theorem is true. So you're not allowed to assume it's false. Okay? That's the mechanics of the proof by contradiction. That's why it's also dangerous, because it's very easy to make a small mistake in your explorations, and whenever you make a mistake, you might come to something fishy, and at that point, the reason you came to something fishy is because of the mistake, but you mistakenly think that the theorem is true. So you have to be very careful in a proof by contradiction. This is sort of a very indirect method of proof. It's sort of like, you give the whole game away. You give up the whole theorem. You assume it's false. You give up the whole theorem, and then you wander around, and then you take it back. Okay? Because you wandered into something fishy, something that's not possible. It's kind of like the ultimate chess sacrifice. I sacrifice the theorem, and then I through showing that sacrificing the theorem results in nonsense, I get the theorem back. The ultimate sacrifice in chess. Okay. So that's contradiction. Let's do another example. And you can try to solve this problem before me. Okay? So, prove that no matter how you choose A and B as integers, it's not possible to get a situation where A squared minus 4B is equal to 2. So you can try to find integers for which this is true. I'm claiming it's not possible. So A squared plus minus B minus 4B is never equal to 2. So it's not equal to 2. So you try to prove it while I erase. Okay, so if you proved it, phenomenal. If you didn't, I'm claiming that contradiction is a great way to prove this. And so let's see how that works. So immediately assume that it's possible. So just like we assume that square root of 2 can be represented as A over B, let's assume that we can find A and B for which this equality holds. Okay. So A squared minus 4B equals 2. Assume for some A and B. Okay, assume it. Well, we're assuming it. Okay. And that's the first step in a contradiction proof. Now we're going to wander around. Well, let's wander around. So what this means is that A squared is equal to 2 plus 4B. Okay. And I just took this to there. I'm wandering around. And what I observe here, this is even. So this is even. So A is even, because it equals an even number. And we know that if A is even, then A squared is even. And we know that if A squared is even, then A is even. Because every even square came from an even number. So A equals 2K. So 2K squared is equal to 4 plus, is equal to 2 plus 4B. Okay, so 4K squared is equal to 2 plus 4B. Divide both sides by 2. 2K squared is equal to 2B plus 1. Oh, I'm getting ready to puke. Okay. Because I claim that here is something very, very fishy. Okay, and now why is it fishy? Because look, on this side is a multiple of 2. 2 times something. So this is even. On this side is a multiple of 2 plus 1. So this is odd. How is it possible for an even number to equal an odd number? Very, very fishy. And that's the end of my proof. The moment my exploration of this fictitious world where I assume the theorem is false, where I assume the claim is false, the moment I come to something fishy, I have immediately proved that this fishy world cannot exist, because you're not allowed to derive wrong, fishy things. So if this world cannot exist, it means that this is not possible. It means that the theorem is proved by contradiction. What a beautiful proof technique. Okay, now let me end the discussion of proofs by talking about proofs involving sets, and then I'll give you some, rules of thumb for. So now we've seen many different types of proofs. You might be wondering, well, we've seen so many different types of proofs. How do I know which kind of proof to pick when? So let's quickly talk about sets, and then I'll give you some tips for picking a proof template. Okay, so proofs about sets. Proofs about sets. So imagine you have two sets, A and B, and there are two kinds of things we like to prove about sets. The first is that the subset relation. So A is a subset of B. Well, we define this as an implication, so you have to prove an implication. It's a nice application of implication. Okay, so this means that, everything that's an A is also a B. So if X is in A, then X is in B, and you have to formally prove this implication. Okay. Now, set equality is the other type of thing that we like to prove about sets. So A equals B, and that means A is a subset of B, and B is a subset of A. So this is two implications, because each subset relationship here is an implication. So this is X is in A implies X is in B, and this is X is in B implies X is in A. So you have to prove two implications to prove set equality, and together this means that X is in A if and only if X is in B. So that's the formal way to prove relationships about sets. You have to prove implications. This is the formal mathematical approach. Now let me also show you a very nice pictorial intuitive approach, which is, proof by Venn diagram. So proof by Venn diagram. And let me show you a fundamental, property that sets obey. Okay. So imagine you have three sets, A, B, and C. Okay. and I claim that, A union with B intersection C, okay, is equal to, so this is the union of A with the intersection of B and C, is equal to the union of A with B intersected with the union of A with C. So this is sort of like, the statement that union distributes over intersections. It's kind of like a distributed law. Okay. Now, I claim that this is true no matter what the sets A, B, and C are. And now let me show you the pictorial. So let me draw A, B, and C. Okay, so here's A, here's B, here's C. Okay. And what is A? So A is this region. So this is also, at the same time, I'm illustrating to you Venn diagrams. Okay. Now, let me repeat this picture and show you what B intersection C is. So here we have A, B, and C. Okay. And let me show you what B intersected with C is. Okay. So B intersection C is the stuff that's common to both B and C, and that's this region. Okay, so this is A, this is B. And what I'm saying is I'm going to take the union of these two. So I'm going to join them. I'm going to combine. If I take the union, okay, now I have my sets A, B, C. Okay. And, I take what's in A and add to it what's in B. So I take what's in A and I add to it what's in B. Well, what's in B? What's in B intersection C? So what's in B intersection C? Part of it has already been added, so I add the rest, which is this part. Okay, and this is B intersection C, and then this is the union of those two, the combination. So this is A union of B intersection C. Okay, so here's a pictorial way of getting that guy. Now let me show you how I get this guy. So again, let me draw my three sets. So A, B, C, A, B, C. Okay. And now let me show you what's A union B. So that's what's in A and B together. So what's in B combined with what's in A. Okay. So this is A union B. Okay, now what's A union C? So A union C is what's in A and C combined. Anything that's in A or C. That's this region. Okay. Now, I want to intersect. That's what this says, intersect. Okay, so what do I get? I have my A. We draw A a little bit bigger. I have B, A, C. Okay, the intersection says take what's common. Well, everything in A is common. Okay, so everything in A is common. Okay, now this part of what's in B is not common. Okay, so I don't take that part. This part of what's in C is not common. But this part here is common to both. So when I take the intersection, I take the common part, which is this part. Okay, which is this part here. That's B. Okay, this part here. Okay. And you will observe that I have shaded the same region in both cases. And so that means that this set, which is in black here, this set, which is in blue here, are the same. They're the same. Okay. This is the proof by Venn diagram. Okay. Now, exercise 1. Go and prove this the formal mathematical way. In other words, prove this set equality by proving the equivalence, the two implications that are shown. And if you're having trouble, look in the book. It's proved in the book. Exercise 1, prove formally / mathematical that A union with B intersection C is equal to A union B intersection A union C. Okay. And exercise 2. Okay, now I'm going to give you 3 sets. So A is the multiples of 2. Basically the even numbers.
B is the multiples of 9. Okay. And C is the multiples of 6. So these are 3 sets. Now I'm going to ask you to prove a subset relationship. Prove that A intersection B is a subset of C. Okay. So now you will see that these 3 sets, it's hard to sort of pictorially represent them. They're infinite sets. It's hard to see what is A, what is B, what is C. So you want to prove this the mathematical formal way by proving this subset relationship using implication. So what you have to do, you have to show that if X is in A intersection B, then X is in C. And I highly recommend contraposition. But you prove it any way you want to prove an implication. The important thing to realize is that proving this subset relationship is equivalent to proving an implication. Proving this equality relationship is equivalent to proving 2 implications. This relationship holds for any ABC. This relationship is holding for these 3. Okay. And so let's talk about picking a proof template. Okay, quickly. How to write a good proof? Now remember, a proof is some kind of an essay that is supposed to convince the reader of something. And if it's not well written, it fails to convince the reader. Okay, it might leave the reader with some doubts. The proof has failed. Okay, it doesn't matter how correct the proof is. If it fails to convince, maybe because it's badly written, it has failed. Okay, so how do you write good proofs? Okay, so, the first thing you should do when you're writing a proof is state your strategy. For example, we're going to use a direct proof. Okay, remember, a proof should have a logical flow. Think about those movies where, jumping back and forth between storylines or jumping back and forth in time. Very hard to follow. Readers, go from the beginning to the end of a proof linearly. So you must have a logical flow in the proof. And, don't try to make things overly complicated. Keep it simple. Your proof has some key idea that should be clear. Okay? So avoid unnecessary notation, avoid excessive symbols. Don't try to show off in your proof. Your proof must convince, must leave the reader with no doubts. Okay? Justify every step. The reader must have no doubts. Okay? So if it's so obvious, don't say it's obvious that. If it's that obvious, give a quick explanation. Unless it really, really is obvious that, 2x is even. You say 2x is even. Okay? But otherwise, don't leave the reader with doubts as to why is that so obvious. Give the quick explanation. Okay? And your proof. So if it's a direct proof, you assume P. Now you need to prove that Q is true. Okay, so you say, and so we have proved that Q is true, concluding the proof. Okay, and last step, but very important, read your proof, check it for correctness, edit it, simplify if possible. Okay, now let's talk about picking a proof template, so picking a kind of proof. There's some, creativity there. There's something to be said there. So what I'm going to do is I'm going to present you with a situation, and I'm going to suggest a proof method. Okay, so we're mostly talking about, implications, but all kinds of other proofs also crop up. So let's start with an implication, P implies Q. We typically say that P is the assumption and Q is the result. Now, if it's obvious to you, if it's very clear how the result follows from the assumption, so the assumption is P, the result is Q. If the result clearly follows from the assumption, direct proof. Okay. Now, on the other hand, sometimes it may not be obvious that how the assumption produces the result. But it might be obvious that if the result is false, then the assumption would be false. Okay, contraposition. Okay. Now, here's another situation. You want to prove that something exists. Okay, that's usually relatively easy. Prove that a unicorn exists. Go and find a unicorn and bring it to me. So, show an example. Okay. You want to prove that something exists? Show an example. You want to prove that something does not exist? Much harder. Okay. Prove that unicorns do not exist. So, what you do, you assume that there's a unicorn and then explore around and end up in some kind of dilemma, some kind of contradiction. So contradiction is usually the way to prove that something does not exist. Assume it exists, explore, come to a contradiction. Okay, you want to prove that something is unique. Again, very similar to proving that something does not exist. If you want to prove that something is unique, basically what you're saying is I have something and I want to show that there does not exist another thing like that. So you're trying to prove that something does not exist. Contradiction is a good idea. Okay. You want to prove it's unique. So you have something. Assume that there is another thing like that. Okay. And then come to a contradiction, which means that that assumption is false. There's no other thing like that. It means that what you have is unique. Okay, you want to prove that something is not true for all objects. So it's not true for all objects. Okay, so all you have to do is find one object where it's not true. Okay, show a counterexample. Okay, so that's a counterexample. Someone makes a claim, and you want to show that it's not true for all objects. Find a counterexample. Okay, find one example where it's not true. Okay, you want to show that something is true for all objects. Okay, that's much harder. And we'll talk a little bit about that next time, but what you have to do is you have to consider a general object and show that it's true. Okay, so you can't limit yourself by saying, I'm going to consider this particular kind of object and show that it's true. You have to show it for all objects, so you have to show it for a general object. So show for a general object. Now, if you want some practice in picking the right proof template and getting used to that whole notion of looking at a problem, trying to figure out which situation you're faced with, and then pick the right proof method, try exercise 4.8 in the book. Solutions are on the web. Okay? Signing off. See you next lecture.